thinking about environmental sustainability, and especially with the coming proliferation of Internet of Things devices and so on, nano geometries become interesting because it minimizes the material impact, right, on the body or the environment, because the amount of active electronic material is absolutely minimal.
Welcome to Stories from the NNI. This series features voices from the U.S. National Nanotechnology Initiative. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. I chatted with Dr. John Rogers, Founding Director of the Center on Biointegrated Electronics and a professor at Northwestern University. We discussed his research, the importance of multidisciplinary interactions, and mentoring of students. John, can you tell me a little bit about your work?
Well, yeah, I'm a material scientist. I'm an academic focused on research on new materials and in particular advanced biomedical devices. What we're trying to do is create foundational understanding and technology capabilities for biocompatible forms of electronics. If you think about the integrated circuit as it exists in consumer gadgets, great for devices like your smartphone. But if you want to think about ways to leverage that kind of technology sophistication in biomedical platforms that can sort of integrate with the human body to provide advanced diagnostic or therapeutic functionality, you immediately realize there are huge differences between those kind of man-made circuits and, say, biological circuits that exist in the brain. A lot of that has to do with radically different classes of materials in those two systems, but it also relates to differences in mechanical properties and geometries as well. Computer chip is flat and rigid and hard. The brain is soft and curvilinear and textured. And a lot of what we have done over the years is to try to develop foundational electronic materials, leveraging principles of nanotechnology to create biocompatible, soft, flexible electronic platforms that have real utility. So our research, we move all the way from novel materials to systems that we can deploy and optimize around existing unmet needs in clinical medicine.
That's a great introduction. Tell us a little bit how you got involved in this type of research.
Well, I guess my interest in flexible electronics and my exposure to it started when I was back at Bell Laboratories. And there we were developing these kinds of organic semiconductor materials, mainly consumer technologies, flexible displays, for example. And as a result of inbound inquiries from neuroscientists who were interested in the ability to take some of these flexible electronic platforms we were developing for displays and deploy them on the brain. I think that kind of interest really led us to pursue that direction as well. I think that has to do with my own interest in developing technologies that have maybe a broader long-term societal benefit that exceeds what you could do in a consumer technology like a display by addressing important problems in human healthcare.
You talked a little bit about your interest in having a societal impact, and I think that part of having that impact is moving your research out of the lab, and you've been quite successful at licensing your technologies. What advice would you give to other researchers who might want to move their research beyond the lab?
Well, I'd really encourage them to think about that. I mean, I think as academics and as recipients of federal funding, we kind of have an obligation to the broader society. They paid for the research. There's an educational value in it. But ultimately, if you can create new technologies and new jobs and broader societal benefits, that would be a great thing to do as a way to pay back the taxpayers who are funding a lot of this research. We've tried to be pretty energetic about pushing some of our technologies in that direction. It's sort of a Bell Labsian mindset in a sense. What we try to do is deep at a scientific level and is fundamentally grounded in basic research, but around problems and topics whose solutions have a technology consequence to them. And so I think the commercialization aspect is important to us.
Could you talk a little bit about your interactions with the NNI?
Over the years, we've received funding from NSF programs that have been focused on nanoscale phenomena, science and engineering, Department of Energy, DARPA as well. We were part of an insect center on nanomanufacturing when I was back at University of Illinois for 10 years, and that was a very important set of interactions for us. Building these devices involves, innovation at the materials level, obviously, development of nanoscale materials and device architectures that can exploit those materials, but means to do manufacturing are incredibly important as well. And that center, really did, for us anyway, establish a lot of foundational capabilities for manipulating and doing manufacturing with these materials. And those technologies and those concepts really flow through everything that we've done since that time, because they're so enabling in terms of our ability to build prototypes and scale things to, again, levels of sophistication that can have real clinical utility. So I would say there have been a number of modes of interaction with the NNI. Those are some examples.
I'm thinking of nanocellulose. I work a lot with the Forest Service. Of course, they're part of the NNI. I guess you alluded to the fact that looking at a semiconductor or a polymer with semiconducting properties is a different approach to the one that you're taking. So is nanocellulose not a substrate that you would look at?
Well, as a substrate, absolutely, it would be interesting to us. Now that you mentioned cellulose, one of the major research thrusts in the group right now is it's somewhat related to the flexible and stretchable electronic technologies that we've been talking about so far, but is focused instead on biodegradability as the key defining characteristic, and environmentally degradable as well. And so there, a material like cellulose is particularly attractive in terms of Forest Service and thinking about environmental sustainability, and especially with the coming proliferation of Internet of Things devices and so on. A big question becomes, what is the overall life cycle of these kinds of devices, and what's happening with the nanomaterials, and where do the substrates go, and how do you do remediation and waste recovery and so on. One solution is to just build things out of materials that are already environmentally friendly and which will naturally dissolve away. Nano geometries become interesting because it minimizes the material impact, right, on the body or the environment, because the amount of active electronic material is absolutely minimal, in the microgram or sub microgram regime when you're using, let's say, silicon that's only 10 nanometers thick. That's kind of a comment to follow up on your question around cellulose, because we've actually used it in those kinds of biodegradable and environmentally degradable platforms, but where we use silicon and biodegradable metals like magnesium, tungsten, molybdenum as the current carrying layers. So that direction is a major thrust of research going on in the group, and I think it's different than and complementary to the stretchable devices that we were discussing earlier.
Those are all areas that I find personally very interesting, and I have to say, after being out of the lab for many, many years, you, for the first time, made me wish that I was a student again, because this is really just a fascinating area. Could you talk a little bit about how you interact with students?
My feeling is that my own career impact will be dominated by what my students do, when they graduate out of the group and go off and establish their own careers. The kind of educational roles that I have fall in several different categories. One is sort of at the level of graduate student mentorship. You're trying to teach people how to do research, how to think independently so that they can go off and pursue a career effectively. Postdocs who are kind of looking to finish up and understand some of the finer points of how to run academic programs. That's another educational role. The other two are sort of at the undergraduate level. One in the classroom is pretty standard, but I'm also very engaged in undergraduate research, primarily because I had a great experience as an undergraduate researcher, and I think it was that experience that led me on my career path that I'm on now. And I feel that it's my obligation to offer to undergraduates that same kind of opportunity that I had. Classroom education is a key part of the undergraduate experience, and it's an irreplaceable piece of establishing core expertise. But ultimately, that's not the way you're going to operate. Into the future, you're going to be immersed in more poorly defined sets of problems, and you'll have to think independently and be able to work in a way that's a lot more similar to that in a research lab. And giving undergraduates a chance to experience that is very important because for some of them, it will open their eyes to a career that they might not have thought about. Or for others, they may realize that that career path is not for them, and it can be equally valuable in that sense. We probably average between 40 and 70 undergraduates in the group at any given time. For the undergrads, it gives them an opportunity to join in and get engaged in scientific research and discovery and engineering development. And I think over the years, it's been very gratifying for me personally to give them that opportunity and to just watch where they end up in terms of their careers. I think it's a hugely important function, and that's kind of my mindset. I mean, I think the only downside for me is I end up writing hundreds of letters of recommendations to grad schools because all the undergrads, but that's fine too.
Well, that was great, and I just couldn't agree with you more. I mean, my undergraduate research experience is what drove me to go to grad school and set my path as well, and I agree with everything you said. That was absolutely fabulous. I appreciate so much your time.
Thanks again for the opportunity.
Thank you for listening to this episode of Stories from the NNI. If you would like to learn more about nanotechnology, please visit www.nano.gov and check back here for more stories.